Swayam Prabha. Digital India. Educated India.
So, we stopped at this point in the last class. We explained what the instruction fetch unit does. It can bring more than one instruction at a time. The register status indicator, there is an entry for every register, and that if that entry is 0, that means the latest value is there in the register file. Otherwise, it is in that it is the execution unit number which is currently executing. And then there are reservation stations marked red. So, if a instruction has to wait for some answer, it will wait there and it will know which unit is having that, and then every execution unit, when it finishes, it puts the result in that common database, and that along with the unit number. So, that the result along with the unit number will go to the register or memory, and on that way it will also go through that purple path, and every reservation unit can see that, right. So, if the reservation unit is waiting for somebody, then it will get it here itself before going to the register file, and this is precisely what we told as the operand forwarding. Okay. Now, we will now go and explain through an example how this hardware is going to take care of the raw hazard. I almost explained the operand forwarding, we will see with an example the var hazard and the wav hazard. It will also do register renaming, it will also do some renaming, and it will handle these var and wav hazard, right, and all these things we will see using an example. Okay. The instructions are fetched one by one and decoded one by one, in the sense that in one cycle there will be many instructions that will be decoded, and we will find the type of the operand, and if there is an execution unit which can do that, it will be pushed to that execution unit. Okay. So, there are multiple execution units. It is not necessary that every execution unit will do every operation. So, there can be 1-2 units specifically dedicated for load and store, there can be 2 units specifically dedicated for integer and logic arithmetic, there can be a unit dedicated for floating point, for multimedia, etc. right. So, I will fetch one by one, in the sense I will fetch all the instructions, right, but I have to, in one cycle I will process it in such a order that I will go and allocate, if there is an, I will decode the instruction, and if there is an execution unit which can handle it, I will put it in it. Okay. So, in one cycle this instruction fetch unit can process more than one instruction. Please also understand that I had to process the instructions one by one, because then only I will understand the data dependency. You understand, right? Then only I can understand the data dependency. So, let us go. The register status indicator again indicates whether the latest value of the register is in the register file, or it is currently being computed by some execution unit, and if the latter is true, that is, it is computed by some execution unit, then the register status indicator will store the number of that execution unit, so that somebody who wants to use that will know which execution unit is currently processing it. If all the operands are available, then the operation proceeds in the allocated execution unit, else it will wait in the reservation station of the allotted execution unit, and it will be pinging the common data bus. Okay. Every execution unit, once it finishes, it will write the result along with the unit number, because if somebody is waiting for it, they will know, okay, this unit is writing, onto the CDB, which is forwarded to all the reservation stations through this purple thing, and it to the register file and memory. Okay. I think we have done it 3-4 times, now you will know almost by heart. Okay. Now, let us see. Okay, we will take. So, these are the 6 instructions that needs to be executed: add R1, R2, R3, store R1, R4 plus R50, store the result of R1 into R4 plus 50, add R1, R5, R6, subtract R7, R1, R8, store the result of R1 to R4 plus 54, add R1, R9, R10. Okay. So I have just restricted, no, there are many things that, let us see how it is going to execute. Now these instructions are processed in one cycle, okay, 6 instructions are processed in one cycle. Let us assume for the sake of argument that these are all the reservation stations. Currently all this, there are 6 units, let us assume that there are 6 units and all the units are currently empty, right. Now we are going to start executing and the register status indicator are all initialized to 0. That means the latest value of all the registers, right, are available in the register file. Okay. So this is one snapshot of the code, we will just take it and see how it is going to get executed. Now what I am going to do is, I will give 6 slides. In the 6 slides I will tell you what is happening to each one of these instructions. But in practice what will happen is, all these 6 instructions will come at a time and all the operations that I am going to talk of in the next 6 slides will happen in one cycle. I need to get more than one instruction to execute per cycle. Okay. Are you able to follow what I am trying to say? Right. Now what will happen? First add R1, R2, R3. Now R2 and R3, what is the value of R2 and R3? They are zeros. R2 and R3 are zeros. That means they are available. So immediately what will happen? It will be allocated to unit number 1, look here, right. Now where is the latest value of R1? It is not in R1, it is currently being computed by unit number 1 and that is why you get this 1 here. So the moment add R1, R2, R3 comes, R2 and R3 are checked, they are all zeros, that means the latest value is available in R2 and R3. Now what you need to do? I am computing the value of R1 here, I am going to add R2 and R3 and the answer is going to be 1. So there is an addition unit, so I will now give it to that addition unit to go and fetch the data and do that, okay. And but I should tell the instructions that are following, hey Baba, R1's value is not in R1, it is currently being computed in instruction unit, execution unit number 1. Are you able to follow? And that is why I have put for R1 the value 1. Okay. Now, right, now next, all of you followed this? Very clear? No doubts? Okay. Now in the same cycle, please note it is not going to be another cycle, in the same cycle now store R1, R4 plus R50 has come, right. Now what is, right, now what is this store going to do? It is going to read from R1, please it is also going to read from R4. If R4 is being computed by some fellow, I should, no. So it is going to read from R1, it is also going to read from R4, please note, because I need to compute the address, right, and then it is going to store in R4 plus 50, right. Now R4 is available to it, right, R4 is available to it, fine, but R1 it comes and sees the register status indicator has 1. That means the latest value of R1 is currently being computed or is going to be computed in execution unit 1. So it will go and say I will wait for 1. So it is waiting for 1. So the I2 is allocated to execution unit 2, but it is not proceeding, it is waiting for the result of 1. You all understand how I got this W1? Obvious, right? So I come here, I need to read R1 and also R4. This is very, very important. Please note that I have to read R1 and also R4. Now when I am trying to read R4, R4 is already available because its status indicator is 0. So R4 plus of 50 I know the address, right. Now I have to write into that address. What should I write? R1 I have to write. Now where is R1? R1 is not in the R1. It is currently being computed by execution unit 1. So I am waiting for it. Fine, followed? Any doubt? Now what is going to happen? I am going to get add R1, R5, R6. Please note R5 and R6, they are available, right. So we can start execution, but now I make the register indicator 3. I allocate add to instruction execution unit 3 and I say the latest value of register 1 is now in 3. Subsequent instructions after this fellow, if they want to read R1, where should I wait for? I should wait for 3. Please note that this I2 is already waiting for 1. This I3, whatever is going to follow I3 will now start waiting for 3. I do not need 1 anymore here, because from now on if somebody wants to read R1, he has to look at execution unit 3, because the latest value of R1 for these instructions are to be are available with execution unit 3, is being computed in execution unit 3. Are you able to follow, right? So that is why I make the register indicator 3. Is that fine? Okay. So let me just do it once more. So I start with, this is the program that I want to execute. Please note, please give undivided attention, right. Now I get add R1, R2, R3, R2 and R3 are already available in the register file, because R2 and R3 are zeros, right. So now this instruction, all the operands necessary for this instruction are available, so I can start executing the instruction. I start executing the instruction in execution unit 1, but in the register status indicator I say that the latest value of R1 is not in R1, but it is in execution unit 1. Next step, I get store R1, R4 plus R50. So I have to read two values, R1 and R4. R4 is already available, correct. You know why I have to read R4, right? I have to compute the address. So R4 is already available. R1 is not there. Where is R1? It is in it's currently computed in execution unit 1. Who is telling this? The register status indicator is telling. So I allocate this instruction to execution unit 2 and make it wait for 1, right. It is waiting for 1 and it is allocated to 2. Now the next instruction, add R1, R5, R6. R5 and R6 are available. So and there is an execution unit also available. So your third instruction set can start executing in the execution unit 3. Now for subsequent instructions which is going to use R1, R1 is no more in 1, R1 is now in 3. So I go and erase 1 and put 3 here. Are you able to follow? It's a very jujube thing, okay. Right. It is not even 1 by millionth of your pulley problem in physics, okay. So now sub R7, R1, R8. Now R8 is available, R1 is not available, it is still in 3. So the fourth instruction will be allocated to execution unit 4 and that will be waiting for the third fellow to complete, okay, right. Now and the latest value of R7, where it is going to be there? It is going to be in 4. So your register status indicator is now updated to 4. Now this fourth instruction cannot proceed to execute because it is waiting for R1 and that R1 is currently computed by execution unit 3, correct, and the result of that is going to be written in R7. So the register status indicator for R7 now stores 4, because somebody else wants R7 beyond, then they have to wait for 4 to complete. You are okay? Is it fine? Now the next is it okay? Any doubt? Palagat, fine? Can I proceed? Yes. Okay. Now next one. Now store R1, R4 plus 54, right. Now I have to read R4 and I have to read R1. R4 is already available because the register status indicator is 0, R4 is already available. but R1 is currently being computed by whom? Execution unit. R1 is currently being computed by execution unit 3. So I will go, I5 will also now go and wait for execution 3. Are you following? R1 is currently being computed by execution unit 3, so I5 should also wait for execution number 3. Right? Now, next is add R1, R9, R10, right? R1, R9, R10. Note that R9 and R10 are available. Correct. So this will start executing in his execution unit 6, and the latest value of R1 beyond that somebody wants will now be available in execution unit number 6. Okay. Do you all get this? Now what is happening? All these operations should happen in one cycle, then only we will get that superscalar architecture, right. Now how do we construct such a fetch unit? That I will keep it for computer architecture course. Okay. We will not deal it in computer organization course. Okay. That is a really advanced topic, right, how to go about doing it. But this is going to happen, and when it happens, now what are the things? Please note that I1, I3 and I6 are executing while I2 and I4 and I5 are waiting. Please note that I6 executes before I2, I4 and I5. I3 executes before I2. That is why we call it as out of order execution. Out of whose order? Compiler's order. Compiler has given some order, but we have now violated that order and we are going out of order execution. Okay. Now all the fellows who have the true dependency, or what we call as true dependency, is equivalent to raw, right, read after write. All those 3 fellows are waiting, they have true dependencies. These 3 fellows are waiting, right. Let us go back. These 3 fellows are waiting. The one this fellow is waiting for 1 to complete, and these 2 fellows are waiting for 3 to complete, correct. So the true dependencies are handled. There is so this hardware, what did I tell? This hardware has to handle read after write and write after read and write after write. Read after write, it is handled here. If I am dependent on a previous instruction and that instruction is currently being computed, I will wait. Now what will happen? When 1 finishes, it will write the answer onto the common data bus, into that purple bus we saw, and 2 is waiting for 1. Answer 1, the moment it sees 1, it will go and grab that and it will start executing. Similarly, when 3 finishes, it will write the answer on the common data bus. The moment 4 and 5, they are waiting for 3, they will be pinging the common data bus. When it comes, immediately it will start executing. So when the answer is going to the register or memory file, it is also forwarded to this and they will catch and start handling. So read after write hazard is completely handled here, and this is how operand forwarding works. Any doubt in this? No doubt, right? Yes or no? Can I proceed? Any doubts? No. Now now I am having out of order execution. How is the var and the wav hazard being handled? How is the write after read and write after write hazard being handled? That is quite straightforward. Now what has essentially happened? I1 is executing, I2's R1 is waiting for unit 1, okay. I2's R1 is actually waiting for unit 1. I3 is executing, I3's I4 and I5's R1 are basically waiting for unit 3. That means what? I have renamed these R1s with U3 and this R1s with U1. Are you getting this? So, and similarly now subsequently if there is an R1 here, it will be waiting for unit 6. So what is this? This R1 got renamed by U1, these R1 got renamed by U3, correct, right. So register renaming happens by default. correct. Then what happens, once the instruction finishes, it will write into a common data bus, and it will also go and see if there is any register waiting for it. For example, when the 6th instruction finishes, right, it will go, and if this value is 6, all the value that is 6, it will go and make it 0. That means 6th instruction is completed, the latest value of R1 is in register, no, it is in the register file, it will go and make this 0. So when an instruction finishes, and if there is any register status which is indicating that fellow, right, when an unit finishes, if that fellow is there on the register status indicator, then it will make 0. For example, if 4 finishes, then it will go and make this 0, unless somebody comes. If 1 finishes, it will not make this 0, because by the time 1 finishes, this already became 6. Right. So whenever I am writing something into the register file, where unit K is writing into the register file, it will go and check all these register status indicator. If any of those fellows have the value K, it will go and make it 0. Fine. So what has happened here? Your operand forwarding happened. Your waiting for a result when there is a true data dependency, that happened. And wherever there was a named dependency like var, wow, for example, there is a var between 2 and 3, 2 is reading while 3 is writing. The var hazard between 2 and 3 has been resolved by renaming 2, right. The wow hazard between the var hazard between 6 and 5 and 6 and 4 are got out by U3, renaming this. So there will be, and right, are you getting this? So there will be no all the write after read hazard just disappears, and this renaming happens in fact. Okay, are you okay with this? Okay. Now what happens is, now when I am writing to the register file, when I am writing back into the register file, please note that this 1, 3 and 6 are writing to R1, okay, 1, 3 and 6 are writing to R1. Now 3 may finish before 1 or whatever, there could be some other 1 here which is, suppose we are waiting for R5 somewhere, essentially 3 may finish before 1 and 6 may finish, because here all the fellows who are writing on to R1 are executing simultaneously. But it may be the case where one fellow needs to wait also. So then what could happen is, so what we have after this is something called a reorder buffer. Reorder buffer. This will be in the path, this will be in this, sorry, this is called rob reorder buffer, that will be here. So the instructions as they finish, right, the instructions as they finish will be loaded into this. For example, in our case I1 will finish I1, then I3, then I6, I1, I3, I6 will finish in one slot. So I1 will be here, then there will be one gap, then I3, then 2 gaps, then I6 will be here. Then your I2 will finish, I2, I4 and I5 also can finish, I2 is a store, maybe I4 can finish and so on, right. So the moment I finish, I go and commit all the instructions above it in one shot, okay. So that is the reorder buffer, because what will happen is that at the end, at this point, see after 6 when I am viewing the result of R1, it should be the answer got by 6. I am taking care of all the execution within the microarchitecture, but when I am writing to the register file, I should have the latest value there, right. So what I do is, even though I complete instructions earlier, I keep it in a reorder buffer, and as and when an instruction finishes, all the instructions, all the set of consecutive instructions from the top, I go and commit it. Okay. So I1 finishes, I3 finishes, I6 finishes. The moment I2 finishes, I1, I2, I3 will be committed. The moment I4 and I5 finishes, I4, I5, I6 will be committed. That will do in one shot. Okay. Right. So by using this reorder buffer, I will also get a consistency in my register file, so that when I am looking at this point, when I am looking at this point here, I will get the latest value of R1 when I want to read it. Okay. Right. Yes.
What is the necessity of us committing the instructions as soon as you find that the top few of them are consecutive?
It's no more necessary, right? I want to have reorder buffer. Reorder buffer is also of finite length, so I don't want a reorder buffer. I can't have infinite length of reorder buffer. So when I find some instruction can be committed because all the instructions above it are completed, I would like to go and flush it off. The reorder buffer is of a finite size. So what should be the size of the reorder buffer? Now 6. At any point of time 6 instructions will be executed. So I will have it as 10 or 12, so that some instructions can wait for long, so the other instructions can proceed. So I will keep on populating that reorder buffer. Once it finishes, I have to go and flush it. Okay. So the construction of the fetch unit and the construction of the reorder buffer are topics of advanced computer architecture. So if you take the elective on computer architecture, you are expected to be taught on this. This is too large for this. We don't have time for this, but you can go and read how this instruction fetch unit can fetch 6 instructions at a time, resolve it. So again logic, okay, it's basically logic. You can start designing, you can use your Karnaugh map and also design that. Okay, and then how do we go and commit? How can the common data bus in a single cycle has to commit many instructions, and how the reorder buffer works. So these things are, you can design it. So the concept is this, but you could have different ways of handling that. Okay, right. Question.
What's the meaning of reorder buffer committing something?
Reorder buffer committing means that it is there in the reorder buffer, it is waiting for some instruction about to finish. Once it finishes, I flush it out and put that value into R1. So that's what we mean by committing. Latest value of R1 will not be in the R1, it will be in the reorder buffer. Once this is over, then I will go and commit it in R1. So some interesting points come up. The thing is that when the register status indicator is 0, right, when the register status indicator is 0, that means the latest value of R1, as far as we have considered so far, we said it is in the register file. It need not be really in the register file, it can also be in the reorder buffer. So I have to go and check the reorder buffer, hey, R1 is there, no, then go back to that. Okay. So if you guys are interested, then what you can do is that you need to learn a language called BlueSpec. I am writing above here, www.bluespec.com. You learn a language called BlueSpec, and then look at our Shakti program, where we have done a superscalar thing. So you can actually go through the code and see how we construct reorder buffers, how do we construct instruction fetches. Damn tough thing, okay, right? But then the language is so expressive that you can understand it quickly, right? But you have to learn the language, BlueSpec. If you have to do it in a low-level language like Verilog or the hardware description language you did. See, please note that this is to be this is not a C program, correct? Instruction fetch, the logic I am talking, all these are going to be realized on hardware, right? So I need to write the logic for the instruction fetch, I need to write the logic for the reorder buffer. So that's not going to be a joke, okay? Verifying this, see actually again I repeat, right? This is not software. What happens in software I already told you, right? You make a bug, now you make the user find out what the bug is, you correct all the bug and resell to him as a next version of software. But in hardware we can't do that, okay? So how do we even verify that this is working correctly? Already we have seen atomic instructions, correct? So where we have seen race conditions, this and this trying to go in parallel. Now in hardware this is going to happen. Now I am going to get multiple instructions, I have to see how those race conditions should be avoided, synchronization to happen, lot of things come up there, and that is really advanced. Okay, so if you look at, so you can go and look at our out of order implementation, say summer, if you can learn this, then next year you can look at it and appreciate how it is being done. Okay. So we have handled all var, vav and raw. We have done operand forwarding, we have done register renaming. Okay. So what is not taught, which is also not taught everywhere in the globe as a part of your curriculum, is how this instruction fetch unit and the reorder buffers are basically designed. Okay. The real digital design. Then everything else is taught.